what's being shown here? I suspect it's pretty hard for you to tell. I wouldn't be able to tell if I didn't know the answer. Until we change the color map here. So with the properly chosen color map, we can see very easily that this is land around Florida and water nearby as well. So I think with this one anecdote, we can see clearly color maps can have a big importance. Okay, so most of my talk here, I'm going to be talking about what makes a good color map. So just a quick disclaimer to start. I'm going to talk about both facts and opinions. There are both on this. This is, there's science behind it, but this is also a subjective thing when it comes to design and art, you know, presenting stuff like this, communication, there's subjectivity too. And of course, anyone's particular data set or application is going to have particular considerations. I claim that the basic function of a color map is to represent data with no preferential values as a basis. We'll talk about exceptions to that. So all data should be perceived as equally important. Therefore, changes in value should be perceived uniformly across the color map. So to talk about this further, let's first talk about color spaces. Color spaces are used to represent color in 3 dimensions. You can make different color spaces make different choices for what these 3 dimensions are. You're probably familiar with the RGB dataset where given color is represented by the amount of red, green, and blue within the color. I'm going to tell you a little bit more about a perceptually uniform color space. And the 3 dimensions that make up this color space are lightness, so black to white, the scale of red to green, and the amount of yellow to blue in your color space, in your color. Okay, so what does a perceptually uniform color space do for us? From a given location to an equally spaced distance away, we're going to see the amount of change in color for that equally spaced distance as equivalent. So an equal distance in the color space looks perceptually equal to us as we view the color. The reason this is helpful is that if we make a color map in this color space with equally spaced points through the color space, we have a perceptually uniform color space that shows us, looks to us as people, looks consistent through the color map. Okay, so here is a metric to look at perceptual uniformity, and generally perceptual uniform color map will not incidentally add or remove information. We may purposefully want to do that, but it won't just kind of accidentally stick it in there. So the metric that I'm using for this is perceptual changes. This is the derivative of the color map through this perceptually uniform color space. So we want this to be a flat line or perceptually uniform so that we're having this equivalence in how the data looks to us across the color map. The 2 on the ends are perceptually uniform color maps. The one in the middle, which you saw earlier in Tom's talk, is our favorite rainbow color map jet, which does indeed have large perceptual jumps across the color map. We can, I think, see the impact of this really strongly in a very simple cone plot. We're looking down on a cone here. We can see the shape readily in the 2 end plots. The one in the middle, though, is, I will say here that the jet color map is adding information to your data set that's being plotted. In particular, where I've indicated with arrows, where there are sharp perceptual peaks in the color map. There are also apparent peaks in the data plot. Oppositely, when there are troughs or plateaus relative to those peaks, the data appears obscured. You kind of lose the detail. Everything's kind of disappeared in there. So what is, should be a cone really looks kind of has these peaks and plateaus kind of going up the sides of the cone instead. So we can pick this out in this simple plot, but it's scary to think what you're seeing when you're actually trying to look at data that's new to you, what visual information is being added that's not really there. And just a note that even nice color maps can wash out detail if not perceptually uniform. I hate to pick on it, but on the left we have a color brewer yellow green color map as accessed in matplotlib. And Oh, good, you can see it on the projector. Relative to a perceptually uniform color map on the right side, we're losing a lot of the detail at the light end of the color map. This is because if you look at these, the perceptual changes across the color map, they are decreasing at that light end, and so we're ending up losing that detail right there. So the cone looks like it's kind of been shaved off relative to the pointy cone on the right side with the perceptually uniform color map. A special consideration within this thinking is the importance of lightness. So research has shown that people interpret spatial structure of data sets best via lightness, like gradients of lightness, as opposed to hue. And so we would like to use this property strategically when you're presenting your data. I'll step through a few basic categories of this now. So here are 5 color maps. Jet is in there kind of as a comparison, but I'll be talking about the other 4 in detail. So these first 4 are sequential increments. These are sequential color maps. So these are color maps that you would want to use when you have data that's incrementing, like from 0 to some amount of rain concentration across a map or something. You want to show a variation in something across a range of values or the presence of something. And you can see that their lightness property, the second row down there, is showing this lightness, just going from dark to light, for example, across the color map. There's also diverging color maps. So these, as opposed to just having one ramp, we have 2, making a peak. And these are, should be used for representing anomalies around a critical value. This would be something like velocity. So what you really care about for something like velocity is positive values away from 0, negative values away from 0. So you're looking at these anomalies away from a critical value. Okay, so how about some examples? Temperature generally is a good example of a sequential data set. It's just a range of values that are telling you information. I've plotted it here with 2 color maps. On the top, we have this same diverging color map from before. And I think there are a lot of nice things about this. We see that it's going from cool colors at the low end of the temperature scale to warm colors at the top, which is nice. It's intuitive. But it is a diverging color map, which really is drawing our eye, I think, to these mid-latitude locations where the white band is. And it's really making it look like there's something important that's going on in the reds versus the blues, which is just not true in this case. In the bottom plot, we still have that intuitiveness of going from cooler colors to warmer colors, but there's no apparent critical value happening. So this is why, in this case, we'd want to be using a sequential color map here instead of that diverging color map. No critical value. Okay, so that was sea surface temperature across the world. Here's another example. We're looking at the sea surface height in the Gulf of Mexico, where I do a lot of my research. The sea surface height is typically presented as an anomaly around the mean sea level. So mean sea level is given as 0, and then you're looking at when the sea level is above that or below that, positive or negative. This becomes very easy to pick off of the map on the left, which is the diverging color map, because they're presented in different colors. But they still have that nice deviation away, ramping down in lightness from that critical value at the middle. Additionally, we're looking at the big red blob here is the loop current coming into the Gulf of Mexico, which is raised in warmer water and then goes out and starts the Gulf Stream. Eddies spin off of this, which are either above mean sea level or below mean sea level, and both of them are associated with a different directionality of the water. So really easily we're able to pick out from here whether it's red or blue, whether it's a cyclonic or anticyclonic eddies. So these are really physically different things that we're immediately able to see because we've properly thought through what we're actually trying to show in this data set. So this is the color map that I would say is properly representing this data set. So one other case that I would like to talk about here, on the right here, this is a cyclic case. So this is where there's really no magnitude associated with the data set. It's a range of values like a compass or a clock, but there's really no magnitude associated with it. In this, here's an example of the tidal phase in the North Atlantic Basin. So this is essentially showing the timing of high tide around the ocean and how it changes around the ocean, different times. But there's no magnitude associated with it. When this is shown in the bottom left plot, and the plot that really has this lightness range associated, it looks like we have this really big important jump happening in the bottom left, going between the yellow and the blue, that is not meaningful in the data set. The top one, on the other hand, just changes hue in a circular way, just like the data is actually changing itself like a compass. So that's kind of a special case. It doesn't come up too often, but I think it's worth mentioning. Okay, so after all of this that I've said about keeping your color map as uniform as possible, there are certainly times where your data set calls for you to break that purposefully. So probably to emphasize some important aspect of your data set. So in this case here I'm showing, well, Veronica is showing bottom oxygen in the northwest Gulf of Mexico. We have the Mississippi River Delta there in the little boot coming out for Louisiana, for reference. Most of the scale is grayscale, showing bottom oxygen, but there is the lower part there is shown with an additional red hue to highlight this important biological range, which is for hypoxic water. So this is showing regulatory agencies really easily, here's the important stuff that's going on. On the upper end, we also see a bound for supersaturated oxygen conditions, which are when phytoplankton are generating oxygen and pumping it in the system at a higher rate than you would normally see there. I'd also like to note that a good color map should, as much as possible, accommodate colorblind viewers. We heard this earlier as well. 7% of Caucasian males have some form of color blindness, often red-green. You can see an example of what this might look like for a moderate form of red-green color blindness in the second row here. And just 2 rules of thumb, I think, to go off of: avoid red and green in the same plot as much as possible. If you really need to have it in there because it's just what makes sense for your thing, saturate it as much as possible in order to make it, that can help people see it more easily. All right, when you're choosing your color map too, choose intuitive colors. Why not? Make it easy for your audience to understand what you're trying to tell them. This is data from a glider, which is going through the Gulf of Mexico. So glider goes up and down in the water. That's the y-axis, depth, and then it's going across some distance in space and time as it moves and is recording, in this case, chlorophyll. So it's really easy to see or kind of reinforce that this is chlorophyll because we're using shades of green. And it's really easy to see there seems to be a layer of phytoplankton near the surface of the water there. Additionally, in our previous plot, we saw sea surface temperature has this cool to warm temperature feel associated with it. All right, so I'd just like to show a set of data to make another point. Let me step you through the data. On the top, we have a model output from the same region in the northwest Gulf of Mexico. It's showing the sea surface height, this anomaly around the mean sea level. Then we have a little ship track there you can maybe just barely see. And the following 3 plots are data from that ship track going down in depth and across the transect. We see temperature, salinity, and oxygen. And I've plotted them all in jet. So I think what stands out to me most is where the yellow is. Yellow tends to be where people talk about their data in jet because it's what's most prominent looking for the reasons we talked about before. So you can really see what's going on in the yellow, especially in those 2 middle plots. The top and the bottom plot, I would say what stands out to me the most is there being kind of a bunch of green that's just kind of washing everything out. You can't really tell what's going on, but there's like a lot of green smearing things out. Okay, so here's the same data instead in matplotlib's new default, Viridis. This is a marked improvement. I don't know, it just looks better. We know that these properties are, that I've been talking, this is a perceptually uniform color map, so that's all taken care of. It looks nice. We're not seeing anything falsely in here. But we aren't able to tailor this if we use a single great default map, color map. We're not able to tailor it to our particular data set that we're showing. So in the top, for example, it's not a diverging color map. We're not able to reflect that in our data just using a single color map like this. Temperature doesn't have that intuitive feel to it necessarily because of the colors. And bottom oxygen, or the oxygen in the bottom plot isn't being highlighted where there's a dangerous level of oxygen. So I propose to use different color maps or artisanal color maps for your data that you have maybe specially chosen or specially made for your purposes. So in this case, I've done the things I've been talking about. I have this diverging color map at the top, the temperature, everything's allowed to have its own color map, and it's really being able to pull out this information. I think one thing that's particularly easy to see again is the oxygen. You can see these fingers of low oxygen coming out from the seabed, it looks like, and that's intriguing as well. If you do this, another benefit of it is background information. I developed these color maps as part of an effort to publish an atlas of data, 10 years of data from a colleague of mine, DeMarco here. And a nice thing about having a particular color map for different data sets is then when you show subsequent transects, subsequent parts of that data, the viewer or you, whoever's looking at it, can kind of recognize the same aspects and compare the plots more easily because you've been able to be trained to look at it in a different way, as opposed to using the same color map for everything. Okay, so how do you make these color maps? VizCM, Nathaniel Smith and Stefan Vanderwalt, as well as now others, have made this tool. And this makes it so you guys, anybody can go make their own color map in Python pretty easily. This enforces linearly increasing lightness over whatever range you set. And it enforces uniform perceptual changes across the color map. And then you choose what colors and everything you go through in space. You can see more information up there. So I used this tool and I made a suite of color maps for mine and now others' purposes. I call them cmocean since I'm an oceanographer. Here they are. You're welcome to use them. They're not limited to oceanography. The names are suggestive, but not meant to be restrictive in any way. So you can see a number of sequential color maps. You can see a few diverging color maps in the bottom right, and a few of the odd cases in the middle there too. This was originally developed in Python. It's available through pip and Conda Forge and hosted through matplotlib. So another example from matplotlib from somebody else. And just as it's very easy to change color maps in your plots, it's very easy to use this package. I've highlighted the code in red that you would need to do to just stick in a color map for this. So while I use Python and I originally developed these in Python, they are available in many other software platforms, a few of which are Plotly, R in the OCE package. Here we have transects of temperature and salinity. MATLAB, there's a MATLAB toolbox that you can use these through. Here's sea ice around Antarctica. General mapping tools. ParaView, and several others are available on GitHub. Okay, so I would just like to leave you with a few thoughts to summarize, to help think about your color maps. Use perceptually uniform color maps and think about lightness and how it relates to your data. Be purposeful when you deviate away from that, I think. Don't just let it happen to you like in JET. It happens, but it's just incidental as opposed to purposeful. Be intuitive and clear in your plots. Consistently use different color maps for different variables, and respect your data. Okay, thank you. Oh, should I?
Hi, thank you for the very interesting talk about colors. And I had a question. Commonly we interact with our color that we choose with alpha, and so then the colors might overlap, and they might also overlap with the background. And I'm wondering what your thoughts are on perceptually sound colors with alpha channels.
Alpha, so you're talking
Like
about
opacity.
transparent?
Yeah, exactly.
In what regard?
So like these all give us, these are good rules of thumb for having colors that are perceptually sound. But sometimes we're going to have an alpha channel, so that means they're going to be blended with the background or with each other sometimes. And I was wondering if there are any rules of thumb for that situation.
I can't say I've thought about that much. I've done a little bit with changing opacity, but not. I haven't thought about that with the background. I'd be curious if other people have thoughts on it, but that hasn't come up for me. Sorry.
Thank you.
Yep.
I wonder if you have any preference or any situation where you choose to use a continuum color map such as this one or a discrete one. I think you showed some that are discrete also.
Oh, okay. So you mean like contour-filled discrete chunks versus yeah. Did I have examples?
I think you have some discrete ones.
Right. So he's asking about when you should use. Yeah. Here, Clark used some here. Yeah. So discrete chunks versus a continuous color map. I'm not sure I have a rule of thumb for that. Well, okay. Generally, I do try to present the data itself, so like p-color mesh in matplotlib I'm using usually because it's like it's showing every model output or data point that I have if it's structured data. Sometimes I will use contours as well if it's just I really need to be able to pick out the boundaries of things more easily. And I definitely use overlaid contours as well. You saw in my in the example for the Cyclic color map. A lot of steps here. But now I'm committed. Okay. So in this, overlaid contours can also play a role, I think, in addition to just thinking about discrete versus continuous color maps, adding additional information with contours. But yeah. Yeah. Oh.
So the last time I played this here, what we do clearly increasing color maps.
Oh, yeah.
They also added support for diverging color maps.
Okay, Nathan asked, is Viscum had just been sequential color maps. Can you do diverging? And I haven't really kept up, though. I get the emails. I believe there's a pull request for making diverging color maps natively in Viscum, but I'm not sure if it's integrated yet. And now I'm going to go back. I did for the diverging color map. I basically stuck two together, like flipped it and stuck two together. So. I did it a little bit ad hoc, but I believe that functionality in Viscum is on the way, if not there now.
What about Cyclic?
Cyclic, I just set the lower bound and the upper bound of lightness equal, and then went around a circle at the single lightness level. So it's still perceptually uniform around without changing lightness. What?
So if I want, say, 5 different categories which are equally far apart, I guess you could just find five points, make sure they're equally far apart. Is there some like built-in functionality, easy way to do this?
For categorical, I'm not sure I caught all that, but I didn't talk about it because different categories don't have a magnitude relationship to each other. So you could certainly, take a color map, and if you have 6 categories, just take, split up and get 6 values across. But I would probably, in that case, actually use the cycler type thing, or what Seaborn has for kind of complementary colors that look nice together.
So, in your suggestion, what should be the ideal thing?
What's that?
In your suggestion, what should be the ideal thing? Like more colors in the scale or less colors in the scale?
Oh, okay. So you're saying how many colors do you run across?
Ideally should be, and if we have more colors, isn't what it will happen that the lighter colors will be overshadowed by the darker colors?
So the colors should all be the perceptual uniformity enforcing that happens in VizCM should account for all of the differences in how colors are perceived by people. That's the point of the color space in the first place. So, and then you only have access within the color space as you're making your color map to the colors that exist within those parameters as you're making your color map. More colors, I think, is considered to be better, like going through more hues. At least in theory, you have the ability to pick out more. However, lightness is that range in lightness, like having a large range from like ideally black to white across the whole color map, I think makes a bigger difference. And so that's why I still have color maps that, like this one, don't range through color, different hues, just use that wide range of lightness to show the contrast, and instead gives you that intuition as a trade-off. So you get the intuition of having greens and having more than one color map to choose from, but you don't have as many hues. So I think it is a little bit of a trade-off. Yeah, and I think I need to cut it off. But please come talk to me if you do have more questions. Thanks.